Okay, today's topic of discussion is transforming quadratic equations, which is section 9.4, and we're going to learn how to graph and transform quadratic functions. So we've already talked about this a little bit, and we're going to lean back on what we did before and kind of talk about parent functions. So remember when we first did this, we talked about parent functions and everything like that, and we did a project on this, and our parent functions here. Remember, for a quadratic, our parent function, there's a couple characteristics of a parent function. The first thing is, our red one here, this is our parent function. And notice the function is just f of x is equal to x squared. And so really what this means is that a is equal to 1, b is equal to 0, and c is equal to 0. Now there's going to be a theme here. There's going to be zeros and there's going to be ones. So if we first look at this, our axis of symmetry for a parent function is x equals 0, so it's right on the y-axis, so that's what makes it a parent. Also, the vertex is at what we call the origin. So 0, 0 is the origin, so it starts at the origin, it reflects across the y-axis, and it's exactly a is equal to 1. There's no modifications at all, and we'll talk about what these b and c does. So if we look at what our axis of symmetry, remember our equation is x is equal to negative b over 2a. And if we put in 0, what we're going to get is we're going to get x equals 0. So a parent function, the vertex is always at the origin. And notice too that this only has 1, 0. And that 0 is the vertex, which happens to be the origin. So it all kind of comes back to this parent function, which starts there at the very beginning. A is equal to 1. There's no change in it whatsoever. B and C are both equal to 0, so that means that there's no changes in that either, because remember we talked about C being our y-intercept. And so there's no other y-intercept other than 0, which is the origin. So the first modification, if you will, of a parabola is what we can do is with the width. So we can change the width of how wide it opens or how narrow it opens. And if we look at this example here, what it's showing us is that we look at the value of a. So in both of these equations, remember we have ax squared plus bx plus c. And remember our parent is just y equals ax squared, where normally a is 1. But if we modify this at all, what's going to happen is if a, or what we call the absolute value of a, is greater than 1, that means our graph is going to become more narrow. And think about this for a minute. The reason that it's becoming narrow is because we're multiplying, and what's happening is it's going to start going up a lot faster. So if we had a value of 1, 3, if we were to multiply that by 2, basically what we're going to get is we're going to get 1, 6. And so what's really happening is it's just going up a lot faster. And if in a similar fashion we multiply by something that a is less than 1, what's really happening is this is a fraction. So we're taking fractions of these values, and so what's going to happen is it's going to get wider. Okay? So if a is greater than 1, so it's a whole number, or it can also be a mixed number, but as it becomes greater than 1, it's going to become more narrow and narrow and narrow, and as a is less than 1, it's going to become wider and wider and wider because it's gaining. So this is gaining slower, that's why it's wider, and then this one up here, this is gaining faster. So because it's gaining faster, it's going to become more narrow, it's going to shoot up a lot faster. Now the reason that we use the absolute values is because if you look at this example over here, g of x is negative 2x. It's still narrower, but this is opening downward. So if this was opening upward, it would probably look like something like this here. So it's going to be narrower than our parent function. It's just that it's going in an opposite direction. So we need to be mindful of whether our a is positive or negative and realize that it doesn't make that much of a difference. Because if we look at here, they're showing you that negative 2, the absolute value of negative 2, is really the same thing as saying 2 which is still greater than 1. So we're always looking at the absolute value, not whether it's positive or negative. And we're only looking at the a value. We're only looking at the a value. That a value of these equations tells us so much about these equations. So first of all, it tells us whether it opens upward or downward, and now it's going to tell us if our graph is going to be wider or it's going to be narrower. So what we're going to look for now is, if we keep this idea of narrower and wider, we should be able to take these and order these from narrowest to widest. So our narrowest function here, is going to be what? Well, it's going to be the a value that is the greatest, or the absolute value of a that's the greatest. So the narrowest has the highest a value, and so that's this one. So h of x equals negative 2x squared, because the a value here, we'll start over here, the absolute value of a is equal to 2. The absolute value of a here is 1/2, and then the absolute value of a here is that implied 1, because whenever we have something like that, it's an implied 1. So we kind of order these from least to greatest, or greatest to least, I should say, because we're going narrowest to widest. So narrowest to widest means which graph is the narrowest. So we know that h of x is going to be the most narrow, followed by f of x, because the next one is 1, followed by g of x, which is 1/2, being the widest because it's less than 1. And so we have to make sure that we're always looking, again, at our a value, because our function, we're just worried about the a value. We don't worry about anything else. So as long as we have y equals ax squared, look at the a value, look at the absolute value of a, and decide, is it greater than 1 or is it less than 1? Again, if it's greater than 1, it's narrow, and if it's less than 1, it's wider, because it's inclining at a slower rate. So the next type of transformation that we can really make on a parabola is basically what we would consider a vertical translation. Now, the vertical translation is basically taking the idea that if we keep our a value the same, so we keep our a value the same, so if we look at the equation, y equals, let's just say, 1x squared plus some c value. Okay, as we increase c, remember we talked about this being our y-intercept. So if we increase this, our graph is going to move upward. And if we decrease this, our graph is going to move down. Because if we look at these, our c value here, this is c equals 0, this is c equals positive 3, and this one over here, c equals negative 4. So this negative 4 is below, so this is our y-intercept here, so our y-intercept here, and our y-intercept here. So it corresponds the right way with our y-intercept, but we see that the axis of symmetry is the same, the width is the same, we didn't change anything about the width. The only thing different is our vertex, or where it crosses the y-intercept. Now, it doesn't necessarily have to be this exact one, but we can see when a is the same, when our axis of symmetry is the same. So when we keep things the same, the vertex is the only thing that's changing, because that's where our y-intercept is. And so as we increase our intercept, well, it's going to go up. And so what we can do is, if I can take a function, so I can take y equals 1x squared, if I add 2, it will move upward from the origin. If I subtract 3, it will move down from the origin. Because remember, this one here, this is right on the origin. And if I add negative 10, well, what happens with that? Well, that goes down because we're negative 10. So it doesn't matter how we do this. We can manipulate this equation by either adding something or subtracting something, and it's just going to go up or it's going to go down. So no matter what we do, as long as we keep the a value the same, and we can move it up and we can move it down. We can move it up, move it down. C is positive, that means it's going up. If c is negative, that means it's going down. Same kind of concept as before. Positive is up, negative is always down. So the first thing that we can do with all this information is we can start comparing graphs. And so how are they different? So the first way that we can do this is we can compare these graphically. Okay? So the first thing that we need to understand is we can look at these two and we can say a couple things. The first thing that we can say is one is f of x is upward and g of x is downward. And we can see that just by looking at the graph. So we see one opens upward, one opens downward. A second thing that we can look at is that f of x is narrower. And the reason that we can tell that is we can see, let's pick a couple points here, that this here opens a lot wider than what this does. Okay? We can see that that opens a lot more than the other one does. And then the third thing that we can point out here is that g of x is higher, or we could say that it's 3 units up. Because if we look at it, this is f of x, and then so g of x is 3 units up, and then we're going to say from f of x. Because now if we move these in a different way and they're not with the origin, we can see that they're still going to be 3 units apart from each other no matter where they're at. So if we move all of these things downward, they're still going to be 3 units apart. If we move everything upward, they're still going to be 3 units apart. So it doesn't necessarily mean that they're 3 units from the origin. It's just that g of x is 3 units up from f of x, and we can see that based on this graph. And so there's 3 things that we can immediately point out. We can talk about whether one faces upward or downward. We can talk about whether one is narrower or wider. We could also say in this second part that we could say that g of x is wider than f of x, or we can say that f of x is narrower than g of x. Those mean exactly the same thing, it's just that we're talking about one in relationship to the other. And then the last thing is we can talk about how they're related to each other from a distance standpoint. And then the fourth thing that we can look at is we can say, okay, is the axis of symmetry the same? Well, we can look since the vertexes are lined, so vertex are aligned, we know that the axis of symmetry is the same. So axis of symmetry, is the same. And so that's also important too, because that shows us that the relationship between the a and b value is exactly the same. And so since the vertex of both of the graphs are aligned, that they have the same axis of symmetry, and that we can see by the vertex alone that g of x is 3 units up from f of x, or f of x is 3 units down from g of x, just depending on how we look at it. Okay, so now what we want to do is we want to be able to compare these equations now without the help of a graph. So the second way that we compare these is just comparing the equations, and we do this the exact same way. So what we want to do is we want to compare, first of all, let's compare whether they open upward or downward. So what we can say is that we know f of x is upward, and we know that because a is greater than 0, and then we know that g of x g of x opens downward because a is less than 0. Because if we look at this, a is 1, and then a in g of x is negative 1. So since f of x is positive for the a value, that points upward, and then g of x points downward because that a value is negative. The second thing that we can do, okay, let's take a look at the axis of symmetry. So the axis of symmetry, the way that we do this is, remember, we use the same equation, x is equal to negative b over 2a, and we can see that for f of x, there is no b, so f of x is equal to 0, and then g of x is also equal to 0, because the b value is 0 for both of those, and when the 0 gets put into here, 0 divided by anything is always just 0. So we can see that the axis of symmetry is the same, so that's good. The third thing that we can look at is going to be our vertex. Now we use the same thing, so we know that our x value is 0, so let's look at when x is 0 in both of these equations. So f evaluated at 0 is going to be 0, and then g evaluated at 0 is going to end up giving us negative 4, because we plug in 0 here, so 0 squared is just 0, then we have negative 0 squared minus 4. Well, that just gives us 0 minus 4, which is negative 4. So we can see, or we could anticipate, that g of x is 4 units down from f of x. Because we know that if it's at 0, the vertex here is 0, 0, and the vertex here is 0, negative 4. So this one we know is the origin, and so we can say in relationship to the origin, well, g of x is 4 units down from that. So those are the three things that we look at when we're talking about comparing equations. And so we look at, is it upward or downward? Is the axis of symmetry the same? Now the third thing that we can look at, or not the third thing, but the fourth thing that we can look at is width or narrowness. So we look at these and we look at the a values. Remember, g of x has an a value that is equal to negative 1. And so we would say the absolute value for g of x of a is equal to 1, because that's negative 1. The absolute value of a for f of x is also 1. So what basically happens is these have the same width. There's not anything different about the width of these two graphs. So we want to look at upward, downward. We want to look at the axis of symmetry, the location of the vertex as far as translation up or down, or the width or narrowness of the graph. And we can tell that by the absolute value of a. Remember, if it's greater than 1, it is narrower, and if it's less than 1, it's wider.